If that is the case, in the yesterday class, we try to look at two of the things named streak lines and path lines. Maybe there is a station which is continuously ejecting out fluid particles. Maybe it might be, sometime back we have seen a static rocket which is burning and continuously ejecting out exhaust gases. So many smoke particles, soot, or these vaporized particles are coming out of that station. Let us assume it. In case, if you can really track, we have seen how hot it is. We cannot really speaking track that individual particles other than color contrast. That is the point of fluid mechanics. So if one can somehow track each individual particle, the trajectory went by that particle, what we call path line, particle line, as a function of time. But we don't really care about each and every individual thing. It might be blue or green, red, yellow, whatever then. But whatever these particles together coming out from one particular station released at that particular T0 or T1, whatever that, you bunch them. This is the way I would like to bunch. That line, what we call streak line, streak line, streak line, and streak line. So the streamlines are the blue line. I'm sorry, the path lines are the streamline. I'm really sorry. Somehow my tongue slipped. The blue ones are path lines. The blue line is path line or particle line. The green line is path line or particle line. The red line is path line or particle line. The other mango kind of color is again path line or particle line for that particular particle. But the blue one, green one, red one, mango one, all these are originated at a particular station at T0, and over the time we would like to really track. So at any given instant of time, connect these particles. How crazy way you would like to connect is up to you. That line we will call streak line. It's not necessary that blue one connected with green, connected with red, connected with mango. You can always connect blue with mango, connected with green, connected with red also. That kind of fancy line, what we call streak lines. But usually at computers, we will always have arrays, pointers to really track, distinguish them from location. Maybe at this height, at this height, at this height, at this height. Whatever those particles originated in the same order, try to connect them. If we are going to do that, we will call streak line. And we try to really look at earlier days example, like there are wind turbines and you place them at different location, flow is coming. I just would like to understand the flow description rather than forces, impact, or and so on, so kind of thing. That kind of study, what we call kinematics. In kinematics, velocities, acceleration, particles, streaks, streams, these kind of things we will understand. Maybe how much deformation, strain, and so on. The first lesson, what we are trying to learn is about these lines. So in that, the same thing, you put it on a simulation. There are these wind turbines are there. You start injecting white color soot at simulation level or even at experimental level. This entire white soot comes from this station. So wait for a while. The soot particle travels, each of the soot particle travels from here to there, here to there, here to there, here to there, and so on, so kind of stuff. Now each of that line where soot particle goes from one location to other location, that means left to right, if I really move my cursor from here to here, that line called path line of that particular particle. Let us stick here, from here to there, along that line. That is what we call path line. From here to there. From here, if I begin, it can come, goes, it can really walks around like that. It can really spin around, it can really come and goes. That line, what we call path line, because I'm tracking only individual particle. Now, if I would like to really talk about streak lines, from this station, all these particles are released and you freeze time, maybe after 5 seconds. Those particles which are originated at 0 seconds travels to this location, this, and so on, so kind of stuff at that 5 seconds. But all these particles originated at the same station from here. Now, if I join those, I will call that one as streak line, because I can very clearly distinguish no white to gray. So I can really say this one is a streak line. But here also there might be a streak line, but only my eyes cannot really distinguish. You might be discharging these particles at 0 second, 1 second, 2 second, 4 second, 5 seconds, 6 seconds, and so on. The 0 second discharge once at 10th second reach this extreme. So I'm going to join them and call that as a streak line, because I can really distinguish white and gray. But there might be particles which are discharged at 2 seconds. Those perhaps reached at 10th second here. They might have went in that way, but I cannot really distinguish. That is the reason I'm not showing that. It's as simple as that. In reality, they look that complicated. So individual trajectory you go, and you are pretty sure that around that white line particle really went, you call path line. Any of these particles originated at the same station, you connect them, then you will call streak line. Clear? Hello?
Yes, sir. Yes, sir.
Wonderful. Now there is something else, another technical terminology. This is what we call streamline. Nothing to deal with particle description, but regarding the flow field. For example, think of in your room, fan is continuously churning air, flow is happening from one location to another location. You have a probe, you start measuring local velocity of the air. How do you measure? You might be having something named hot wires. Earlier days, people try to use that. Hot wire fluid, hot probe, something like that. Hot wire anemometer. Can you see this picture?
Yes, sir.
So that one, or perhaps this one. There is something like a mechanical instrument. There are something like filaments. They are connected and so on, so kind of thing. They will be having different kind of shapes. Sometimes they might be having only this kind of probe. Can you see that? There is something like needles, and these needles are joined by a filament. Right? There will be electrical circuit goes inside that. That might be your Wheatstone bridge. Are you aware of your Wheatstone bridge?
Yes, sir.
So you think of something like application, gas flow passing in the tube. There is a resistance. You try to really maintain the Wheatstone bridge in such a way that based on the gas flow, how much heating happens, how this resistance really varies. Because it removes heat, suddenly resistance drops or increases. That way you calibrate it in terms of potential to really sense what might be the gas flow. This is what you call calibration. That is the way in 1930s, 50s, or maybe 1950s, 1960s, people used to do. Now you have sophisticated measurements, but this is the way engineering technologies developed. You might have learned your Wheatstone bridge just like a physics. Okay, this resistance, where is that resistance, where is, there is a galvanometer, there is a battery, there is a rheostat. We don't really care about that. It's more like a science. But people have something idea when such kind of Wheatstone bridge arrangement really comes, they have certain application in focus. Something like I need to really measure these velocities. I cannot really perceive it. The best way, sophisticated at that point of time, 1950s and so on thing is use these hot wires connected to these Wheatstone bridges so that you can measure velocities. Maybe atmospheric flow is happening. How do you know what is the speed at which it is going? You just insert that probe. You calibrate this bridge. It continuously tells you. That is the way people used to think. Fine. Even nowadays also people use it because this is very tiny probe which you can really connect it. The other way is called PIV, particle image velocity metry. Yeah. Can you see this? Flow is coming in a duct. Flow is going. There is a camera. They spray. They put some particle, aluminum particles, or some tiny glass beads. Record that. From there, they calibrate it. Finally, get images like that. Can you see that? Hello.
Yes, sir.
So you sprinkle particles, glass beads, and so on, which are neutrally bound, like more like your pepper. You sprinkle pepper. You start stirring it. Track this pepper, how it really goes. Based on that, you can get images. That's what you call particle image velocity meter. Maybe thermal fluids, you would like to really get it. That is what you call PTV, particle thermometry, whatever. Okay, we will see. Based on the temperature, you will get pictures. Particle thermovelocimetry is something like that. And that kind of stuff also happens. So your kinematics really helps you to recreate such kind of pictures. Though it won't really tell you forces, all these details, but this kinematics lessons, this is path line, this is particle line, how to really integrate them. Once you get this information, that way it's going to help us, which we call kinematics. There is something like laser Doppler anemometry. Sound waves will be passed, light waves will be passed, how it really scattered. Based on that, one can really calibrate that. The change in your frequencies and so on, one can really calibrate it. Maybe with which velocities, acceleration it is going and so on, so kind of stuff. For all these things, what you really require is something named these kinematics description, especially when you are going to use these hot wires to track velocities. To find that, we usually bring this concept named streamlines. So fan is continuously blowing air. You bring this hot wire into that system. Based on this Wheatstone bridge principle and so on, you can calibrate, you can really get velocity. Now you move your hot wire from one location to another location. So you traverse it so that you will understand what is the velocity along that line. Maybe move vertically, you will understand what is the velocity. You move horizontally, you will measure the velocity. So now think of a situation. There are some imaginary lines on the floor, the blue one. Any tangent represent velocity. That means you have a hot wire and a hot wire. You locate at one location. You know what is the velocity. You move lateral location. You measure the velocity. Now you try to connect these points such a way that there will be some imaginary line will be there. At any point on that line, supposed to give you velocity vector information. Such kind of lines, what we call streamlines. This is way easy to use in fluid, looks like complicated thing. That is the way applied math guys try to use it in 18th century, 19th century, when your instruments were not that powerful. Your Wheatstone bridge might have come in 1850s, 1830s. But well before that also, applied math guys try to really work out fluid mechanics problems. They do not have instruments. How do they really get the information? So they try to really get this information in terms of streamlines, mathematically. Try to construct these lines based on certain fundamental principle. Pick that line, you draw a tangent, at that point is supposed to give you velocity. That means there is a line in three-dimensional coordinate like x-axis, y-axis and z-axis. That means you tinily move from one location to another location, dx, dy, dz in 3 dimensions. That means if you have a velocity at one location, the other location velocity will be v plus dv. So the tangent one tells you the variation in velocity or velocity vector thing. So let us look at animation or video. Then we will have better understanding about this streamline. Am I audible?
Okay.
Yes, sir. Let us look at streamline. Definition of streamline is, it is an imaginary line where on that line the local tangent line represents local fluid velocity. Basically, it's flow velocity measured locally. One has to freeze time. Measure what is the local velocity there. Local velocity everywhere. When we are measuring, perhaps u component at that given instant of time at different x locations, perhaps varying. This is the thing what we are measuring. Now, collect all these velocities means two components. So the tangent velocity always represented by a vector of certain units, certain direction. Now, whatever those lines which are having the local velocity vector tangent to that imaginary line we call streamline. That means on this you measure the local velocity. That gives you tangent velocity vector. You measure local velocity. On that curve, the tangent of that curve represents local velocity. You measure local velocity there. That is the tangent. Now for this curve, if you measure what is the tangent there, the local velocity will be given. So this vector is u at a given x location and time t. And all these measurements one has to do at the same time. Though the positions are different, you have to freeze time. From that curve, if you take tangent, you get this velocity. Streamlines are used to solve equations for math problems. In reality, you do not have any streamline. It's just an imaginary curve. That never exists. So the pictures, whatever on automobiles we see, smoke is moving and so on, these are basically streak lines because you inject the smoke at one location. If it is something like a certain condition steady, all these particles follow only one line. So each particle path line coincides with all these particles instantaneous locus. You have path line, streak line coincides, and in fact if you measure local velocity at that location, you get this streamline also. In case of steady flow, all these streamline, streak line, path lines remain same, but if you really measure for a given pulsatile flows, turbulent flows and so on, these streamline, streak line, path line differs. So whether they differ or they remain same, unless we write math, we will not be in a position to appreciate it. We will see that. So there are some imaginary lines, you just put velocity or you measure, you get velocity, local velocity. Let us quantify path line and streamline. Somewhere in the flow field, we have located a particle A. With the time, this fluid particle travels a path. This means at time t1, the fluid particle is at that location. At t2, the fluid particle is at that location in this space for a given xy laboratory coordinate systems, xyz laboratory coordinate system. The fluid particle at different times located at different positions. So at each position, it might be having one particular velocity on the laboratory plane. So if I am going to measure velocity of that fluid particle, let us call VA. Again, velocity of that fluid particle VA at time t2, and velocity of that fluid particle at time t3, which is again VA. The number might be different. VA value might be different. The notation what we show is velocity of that fluid particle A, which is originated at a given location x0 and time t0, traversing at different locations. This is the way we note, quantify, represent the path line traced by a fluid particle in terms of its velocities, which is equal to dxp of that fluid particle A dt. If we know already the path traversed by that fluid particle, at each and every location, we know the position as a function of, so with the time t, if it is one-dimensional coordinate, just xp component, we have position 1 unit, 2 units, 3 units, 4 units, again 3 units, something like that. So 1 unit, 2 units, again 3 units, and so on increases. If that we are trying to do that, we call that as a path line. And once we know those positions, we can always calculate dxp by dt of that particular fluid particle as velocity of that fluid particle. In the case of streamline, let us put it there. Freeze time measure velocities irrespective of fluid particle A, B, C, D, E, F, and so on. Throughout the field, just measure it. And wherever you measure it, if you are in a position to draw a particular line, how to draw that? That's governed by your mathematical equations when you are solving. Once you know that streamline information, stream function information at mathematical level we talked about, you take tangent on the laboratory plane at given locations. That gives you instantaneous velocity field information you are freezing. That tangent represents
instantaneous velocity field on the Eulerian field.
That means all the fluid particles you are going to look at.
Streamline information with path line. In some sense possible, because you are taking a frozen time snapshot. That means there must be some fluid particle of this. When you are freezing, there must be some fluid particle whose velocity supposed to match with what you measure on the laboratory frame or on the Eulerian field. So typically for Eulerian velocity field, we represent u as a function of x comma t, immaterial of which fluid particle you are measuring, and you freeze at time, so there must be some fluid particle, and let us call that fluid particle as A. So that's supposed to be velocity of that fluid particle A at that given instant of time. Now this fluid particle might have originated at this location at previous time. It might be coming from that location when you are measuring the Eulerian velocity field. Perhaps that fluid particle might be coinciding. But streamline is different with respect to the path line, because path line you always evolve in time, then observe it what is happening. In the case of streamline, you freeze time, irrespective of whatever might be the fluid particles. You don't bring any fluid particle information, but locally measure velocity of all these fluid particles. Whether they are originated at same location or not, it doesn't matter. You just locally measure, draw imaginary curves so that the local velocity is tangent to these curves. If that is the case, what we will say is, because it's a curve, mathematically the way how we represent is, it has a slope of a curve, the streamline curve dy by dx is equal to the local fluid velocity what you are measuring. So the tangential direction. So tangential direction means the local velocity might be having that. It has both v component, v component, and the tangent if you want, which is v by u. You freeze time, pick a particular point on the laboratory frame, irrespective of what type of fluid particles are moving. You just measure local velocity. It always be inclined having an arrow kind of thing. So if I am resolving, it will be having both x component, y component. Let us call x component as u, y component as v. So v by u tells you the slope of that curve, which is dy by dx. So usually people write it in this way: dx by u is equal to dy by v as the equation for streamline
in 2 dimensions.
The equation for path line is velocity of particular fluid particle A supposed to match with your local fluid velocity. In that case, I can always write velocity of the fluid particle as dxp by dt. This represents particle position, how it is varying for a given fluid particle A supposed to match with this. So if I integrate this equation from this location to next instantaneous time, perhaps I will be in a position to track the next information of the particle.
Great. That is the way we calculate that, and any color. So we will close our today's session. So if you are looking anything, such kind of nice lines and so on, so thing, first you need to really understand what exactly are these lines. What is streamline, what is streak line, what is path line. Maybe if you are really going to do it animations and so on, so thing, really getting this kind of color filled pictures, they are not streamlines. Though we use something like streamlined objects, streamlined bodies and so on, they will be either particle paths or streak, because you are going to snap it. Take a picture, click. That means all the particles which are originated at the same location, you are going to really see. So this particle perhaps came from here, this particle also came from here, this particle also came from here. If you say that this is your local station, then this is your streak line. No, this entire thing is my station. Then at any given instant of time, that is the streak line. But definitely these are not streamlines at experimental level. Okay, so in the next class, we will work out some example on path line, streamline.